So when we talk about forces, one of the key things that we try to understand in physics is where do these forces come from? So if we take you and we drop you on the ground, what you'll notice as you walk around is you do get pulled down by gravity. You don't spontaneously float off the ground and disappear. And as you walk back and forth, things are relatively solid. If you come up to a wall here and you try to pass through it, something stops you. Now, when we talked about reactive forces, we talked about this being the normal force. So even though gravity's pulling down on you, the floor beneath you and the wall that you're currently touching exert a force to stop you. Now, the normal force is not actually a fundamental force. It's not a real thing. It's just a consequence of what you see. And things like tension and friction have the same effect. So if these forces are basically almost fictitious, the question is, well, what causes these forces to exist? And that's what we're talking about in terms of fundamental forces. Now, for fundamental forces, we do have three of them. The first is gravity. This is something that we've noticed throughout our observation of the world around us, but basically any two objects that have mass attract one another. So if we have you, say up here, not hitting the ground yet, you'll be attracted to everything that has mass. So if we have some kind of floating object, both you and an object will be attracted towards one another because you won't have mass. Both you and the object will be attracted to the earth or the ground. Both you and the object will be attracted to the wall, so on and so forth. Anything that has mass attracts one another. And that's one of the first fundamental forces that you can see. Now, what defines fundamental force is the fact that it is consistently defined. When we dealt with things like friction, which is probably the best example of a non-fundamental force, we had to deal with a whole bunch of rules. And those rules depended, whether or not we were moving, whether or not we had a force applied to us, so on and so forth. Fundamental forces are a little different. They have a very consistent definition. In other words, we can describe them, usually with an equation. That equation works every single time, exactly as it's written. And if it doesn't, it means we haven't truly found the fundamental force yet. Now, in the case of gravity, we have a fundamental equation which you'll see in the center of the screen, and this is Newton's law of universal gravitation. Now, there are some slightly different formalisms for gravitation to deal with things like relativistic speed, but for the purpose of this course, this one works very well. What this basically says is the force of gravity between any two objects can be found by taking a constant, which is the capital G, multiplying it by the mass of both of the objects that you're looking at, m1 and m2, dividing it by how far those objects are apart squared, that's the r squared in the denominator, and basically they'll attract towards one another on a straight line from their center of masses to one another. Now, you might ask yourself, well, why don't I see this? If I'm sitting at my desk here looking at my computer, why am I being thrown towards the computer? And the answer is, for the most part, this constant g is very, very, very small. It's on the order of 6 times 10 to the negative 11. So what that means is, in order for you to see a noticeable force of gravity, you have to be dealing with things that have a ridiculous amount of mass. Now, in your day-to-day life, the only time you really see gravity is when the Earth pulls on you. And that's because the Earth is real big. It has an absolutely ludicrous amount of mass. Now, at the Earth's surface, we could define r, a radial distance from the center of the Earth to where we are, and we know the mass of the Earth. So what is typically common for gravity in terrestrial systems is we treat the acceleration created by gravity as a constant. This lets us calculate the force of gravity very, very simply, which you'll see now here on the screen. The idea is if the mass of the Earth and the distance from the center to the Earth is relatively constant, we can treat all those quantities together with the capital G to form a single constant, which I refer to as the acceleration due to gravity, a subscript g. In your text, it is probably just referred to as just g, but that's just a matter of personal preference. And so what this lets us do is it lets us calculate the force of gravity acting on small objects on the Earth's surface by taking their mass and multiplying it by this acceleration due to gravity. Now, on Earth's surface, on average, this acceleration due to gravity constant is roughly 9.8 meters per second squared down. That is fairly consistent amongst the surface of the Earth, because if you take a look at the Earth from space, the Earth is smoother than a bowling ball. It's pretty near spherical, and even the tallest mountain, right, even Mount Everest, has nothing on how big the actual Earth is. So it's pretty consistent. It does, of course, vary. If you go up to the International Space Station, the acceleration due to gravity can drop as low as, I believe it's 9.4 meters per second squared towards the center of the Earth. So it does vary depending on where you are, but for the most part, you can take this value as a constant. Now, the nice thing about this force of gravity is it's a force like any other force, and it's consistently defined. So you can use it in conjunction with other effects to solve force problems. Basically, it tells you where one of those forces that you might have to deal with is coming from. Now, the force of gravity is not the only force that you might have to deal with. In the context of Physics 1, we don't talk about any more of them, but there are a couple more that are important. So if you're sitting here on the ground, you don't really pass through it, so there has to be something that stops you. What actually stops you from moving through different objects is actually an electromagnetic interaction. In other words, you're made up of atoms. Those atoms have charged particles in them, protons and electrons, and they actually bounce off the protons and electrons present in the surface. Basically speaking, almost every force that you experience in a day-to-day life, whether you push on something, prevent yourself from falling through something, any of those, they're all mediated by a force known as the electroweak force. The electroweak force consists of two basic parts: electromagnetism, which is the one that causes pretty much everything that you see, as well as the weak nuclear force. Now, the weak nuclear force is in addition to this. Basically, if you have something like an atom, here we go, it's possible for this atom to break apart. This is radioactive decay. The weak nuclear force is actually a part of the electromagnetic force. They're unified together. That basically allows for atoms to split apart. And if you think about it logically, it's not that complicated. Nuclei of atoms are filled with positive charges, and positive charges get repelled electromagnetically. So the weak nuclear force is just extending that electromagnetic repulsion with some different math to breaking atoms apart. Now, the final fundamental force is known as the strong nuclear force, and it basically deals with the opposite thing. If we have an atom and it's made up of a whole bunch of protons, so there's a whole ton of positive charges, and positive charges hate each other and they're always trying to get away from each other, the question becomes what keeps the atom together? And the thing that keeps the atom together is the strong nuclear force. Now, on an oddly related note, there is a particle that mediates this strong nuclear force, and it's almost a joke because you might say, well, there's protons in the nucleus and they're basically glued together. The particle that mediates the strong nuclear force is referred to as the gluon, like literally like glue. Now, in terms of strength, gravity is the weakest force, but it has the longest range, which is why if you're dealing with astronomical problems, gravity is real important. In the middle is the electroweak force. It's significantly stronger than gravity, but its range is not that long. And because its range is not that long, typically speaking, every force on the person or living thing scale is mediated by electromagnetism. We don't talk much about electromagnetism in Physics 1 because electromagnetism is pretty much the entire subject that you would find in Physics 2. And lastly, the strong nuclear force, as per its name, is the absolute strongest force. It's actually crazy strong in comparison to all the other ones, but it has a really, really short range. In other words, it doesn't go much beyond the nucleus of an atom. These forces altogether, as far as we understand it, make up every single other force that has been observed. So things like tension are mediated by electromagnetism. Things like the normal force are mediated by electromagnetism. Gravity pulling down on you is mediated by gravity. And your atoms sticking together is mediated by the strong nuclear force. They're fundamental because they're consistently defined and they make up everything else that you see.